Yeah, so I think we're ready for specific heat capacity. Last week we were discussing, can you remind me what was last week about? Last week, what did we do? I want you active. You're not too
Linear
many,
expansion.
Linear expansion. And I remember I was talking a lot about water and how exceptional water is in its behavior around 4 degrees. And I told you this is not relevant for the lab. I just believe water is exceptional. Today, I'm going to talk a lot about water as well, because it's not only going to be exceptional, but the specific heat of water is really large and it's gonna affect so many, it has so many consequences. All right, the outline is the following. What is specific heat capacity? In general definition, thermal equilibrium, how is it reached and how do you solve a problem where you need to find the final temperature whenever you have thermal equilibrium, because the experiment is about that, and eventually how the lab report looks like. So I think we can do this really fast. 30 minutes, we're done, okay? Unless I need to talk a bit about water, and please stop me if you believe I'm talking a lot about it. So what's interesting about water? Can you please explain why you think that water remains colder in the
It
hot,
has a
hot summer? Yes?
high heat capacity.
Okay, how? Can you try to explain? Reflection. So Mia believes because water reflects light away. Yeah, but I think sand is more reflective, isn't it? It's so much harder to look at the sand in strong sun than to look at the water. And you know that water does not reflect all the rays. You know, some rays would go through. Okay, what do you mean by sand absorbs heat? I believe water also absorbs heat. Like I can heat water on fire directly, and I can heat a metallic spoon on fire directly. We're not talking about light and reflection. How come it takes me forever to heat the water for my coffee, but it takes me few seconds for the spoon, metallic spoon, let's say what kind of metal we want, anything, iron, it takes a second for it to be really hot and you can burn your fingers. Heat capacity. So how do you define heat capacity? Probably Mia can give us a bit. Okay, fine. I totally agree. She said she forgot about it. She knows it's related to that. Okay. Let me show you this, and this could be interesting for you. I don't know if any of you is a swimmer, and I mean by swimmer, open water swimmer. Any of you swim, like swim frequently? So George is trying to say how much heat it takes to change the temperature of something. Yes. All right. So I don't know if you ever went into water, I mean the Mediterranean Sea, in spring or in the fall. Probably you did because you are a small country on the sea. So I suppose you tried to swim in April, did you? Aren't we in April? Anybody swam this weekend? Not the ocean, the Mediterranean Sea. Okay, just a pool. Okay. Anybody try to go into the sea this weekend? All right. Anybody would swim in November? Any one of you swam in November? Okay. All right. Personally, I swim in the sea and I try to swim 12 months a year. And this graph is like printed in my brain. I check it every now and then, especially if I do have a race. That's why I believe that's very interesting. The interesting part is that the sea in the fall is very warm, and even December. There's a competition in December called the Christmas competition. It's very famous, and probably one day you're gonna compete in it. Us old people love those competitions. So imagine the sea in December has a temperature of 20 degrees C. And you know the temperature of the outside weather in December could drop easily down to 15 and sometimes 10, depending on the weather. You see how warm the sea is gonna be? However, if you try to swim in March or April, I doubt this is really 18. Sometimes it's 16. One day I had a race in May, and the temperature was very close to 18 or 19, and you can you can find it out actually instantaneously. You know, there's another chart that would give you the temperature per day or average per week. It was very cold, and swimming in 18 or 16 degrees is really very difficult on the human body, you know. So yes. So how come water stays very warm up to December, and it's actually very cold in May and April? It's due to the fact that water takes a lot of time to heat up, and again a lot of time to cool down due to the specific heat capacity of it, right? This is another example. It's about the Lake Michigan. It takes longer to heat up and longer to cool down, and this is affecting the city of Chicago. All right. Yeah. So it does affect it because it's somehow. All right. What else? I also know that since water has a very high specific heat capacity, it takes a lot of heat to heat up and a lot of joules to cool down. It affects a lot the human body because you know a big portion of the human body is made of water. So it's an excellent, how can I say it? It's an excellent stabilizer of temperature. So otherwise you would be really boiling hot in the summer, and that's really dangerous. And especially people who get dehydrated. Yeah. Can you tell me more, Mia, about it? It's a lot of biology and I'm sure you know more than me. How does water regulate human temperature?
One thing we talk a lot about biology is that water is very necessary because in the heat, like we sweat, but these are like water particles, and then these water particles they kind of like
evaporate to cool the skin.
And this is yes, and it also happens in plants too.
Okay, wow. So I've never considered that. So it's also skin related. I was talking about the whole system, like your body. But yeah, skin, that helps a lot to cool you down. Yes. Anyway, just think of those because you have some conceptual questions in the lab report related to this. Now let me move on to the physics of the experiment. What is specific heat capacity? And this is exactly who said so, George? Yeah, it's how much heat or how much joules is required to increase the temperature of a substance by 1 degree C if we're talking about 1 kilogram. All right. The units could be different. As you can see in here, it could have a unit of joules per gram degree C. So we can be talking about 1 gram, and it could be kilojoules, but I doubt because the values are really low. Even if you change that to kilogram, you're still in the thousand and not in the million. So you don't need a lot of joules. However, to melt or to boil a certain substance, I'm talking about water as well, we're dealing with millions of joules. So just to heat up a substance, increase in temperature only, the joules is reasonable, and you can do it at home, like heat the water for your coffee. By the way, so which means that C is the Q divided by M delta T, and you can see it in the unit. It's Q, and Q is the heat added to your system divided by the mass, which is the kilogram, divided by the change or the jump in temperature, which is the Kelvin. By the way, I need to remind you, can you remind me how you convert temperature C to temperature K? Okay, so you take temperature C and you add to it 273. 0.15 if you want more significant figures, yeah, or 0.2. How about delta K? If I have a jump in temperature in degrees C, how do I convert it to degrees? Yeah, it's equal. So the jump is equal. This is very important, and I'm glad you know this. Okay, which means if you are given delta T in K or degree C, it doesn't matter, and you can easily change the unit like this one. You can change it to K, no problem. It's gonna remain the same. Okay, because we're talking about the jump, either drop or increase in temperature. All right, now let's check those substances. Which of these substances have the lowest or the highest specific heat, and does it make sense to you? Water is the highest, and it's already famous for that. I can think of silver. I've never heated silver before. Yeah, look at iron. Aluminum, usually when you touch it, it's cold a bit, no? I don't know how these would give some applications in your daily life. But yeah, the most interesting thing is water needs so much heat to heat up. All right, I need to mention this before we move on. Every time we say that Q added to the system is mc delta T, this is only applicable when the temperature of the substance is changing. And this is the famous graph related to water. So here I have a change in temperature. By the way, can you remind me at regular pressure, what is the temperature of ice and water? Temperature of ice and water, just to complete the graph a bit, because the graph is a good sketch for us. If we add some values, probably, yes, it is a 0. So at 0 degrees C, this is the melting temperature or the freezing temperature of H2O. What about the boiling temperature? I'm sure you know it. Exactly, it's 100 degrees C. And I'm talking on the regular pressure because, you know, as the pressure changes, this is gonna change. Yes, yes, I know it's depending on pressure. And if you're heating water from 0 to 100 degrees C, this increase in temperature, you need a certain Q to be equal to mc delta T. So it's mass related, C related, and delta T related, which means you can tell how much heat you need from point A to point B. Okay, so this is the amount of heat needed. Same for water vapor. However, water vapor has a different C. So how about I call this C2, and here it's gonna be MC3 delta T. Okay, and I know we're talking about H2O, but the specific heat capacity of vapor and ice are different. So you can find a table where you have specific heat capacity of ice and water, and they're a bit different. If you want, I can check how different it is. And this is MC delta T. Let me call it C1 delta T. Okay, let me have a moment. And if it doesn't take time, let me check if I can find the specific heat capacity for ice, just for you to see how far away it is from water. It should be in this chapter, and I saw it a few days ago. So this, do you see ice? It's half the water approximately. So water is 4,000. By the way, this is kilogram. That's why it was 4 point something back in the presentation. Ice is only 2.2. So it's half, you know? Yeah, so it's so much easier, back to our presentation, it's so much easier to heat up the ice from, let's say, negative 20 degrees to 0 degrees C. And what you have in here is a quantity of heat needed that has nothing to do with MC delta of T. It's a different way to find it. But since we're talking heat and you need that for the course, do you remember how to find Q when something is melting and how to find Q when something is boiling or evaporating? Do you remember any of that from school, or probably you took that in the course? Anyone? If you can't remember, say you can't remember. It's important for me to know. All right. So we need to use the latent heat, and the latent heat is the heat for changing a phase. Okay. So it's, you take the mass definitely and you multiply by the latent heat. It's called LF for fusion, and fusion means melting. And you take the mass and you multiply by LV, and V means vaporization. All right. So it's for evaporation. It's very important to notice from this graph, and I believe the graph is very important. It shows that you either have a temperature change or a phase change. You cannot have both at the same time. You see, temperature change in this case, phase change, and then temperature change and phase change. Let me just change the size of the pen and not the color. So temperature change, then phase change, temperature change and phase change. And they can happen one at a time. You cannot have them happening at the same time. So you have them in steps. And I believe you need that in the course. I'm surprised that you did not do that yet, or probably you're gonna do it very soon. Am I right? Anyway, what we have in the lab is something very simple. We just have a solid, it's basically a metal, at a temperature of around 90 degrees that we need to cool down to a temperature around 30. So we're only gonna use MC delta T. Thermal equilibrium. What is thermal equilibrium? Anybody can explain this picture? It's a very easy something to understand. So what do you understand? It's a bit blurred, I know. Yeah, so tell me. I love examples that are related to daily life because you can think about these every day. They happen. Like I add hot water to my coffee every 5 minutes. Eventually, it's gonna become no color. Like when two substances of different temperature are in contact, we're talking about milk, and the milk is cold, and this is coffee, and coffee is hot. So what happens? The hot one becomes a bit cooler, and the cool one becomes hotter. So I have heat transfer from the hot, from the cold to the hot. So the heat transfer is in one direction. Yes. And what happens at the end? One common temperature. So this is called the final temperature, and this is called thermal equilibrium. Thermal equilibrium is when both become at the same temperature and you have no more flow, or the flow is gonna become average zero, all right? Because the flow is always there microscopic. So you see here, if you have a substance at 0 degrees C and a substance at 100 degrees C, you're gonna have a flow from 100 to 0. That's the flow of Q. If I take this to be substance 1, this to be substance 2, I can easily say that Q1 is actually positive because it's gaining heat, and Q2 is negative because it's losing heat. And you can say that in absolute value, they're equal and opposite. Why? Because whatever a system 2 will lose is whatever system 1 will gain, assuming the whole thing is insulated and nothing is being lost in the environment, right? Now, to find the final temperature, if we assume that both substances, so in two assumptions, one, both substances are the same material and same specific heat, and two substances have the same mass, because I can have a lot of the orange and a very little of the blue, I can say that the thermal equilibrium is going to be the mean of both values. Otherwise, the final temperature or the thermal equilibrium temperature is going to be between 0 and 100, sometimes closer to 0, sometimes closer to 100, depending on mass and specific heat capacity. And there's a way to calculate this by simply saying Q1, Q2 are equal and opposite. You can find T final, okay? This is just an example that I thought would be interesting to solve. We're talking about two metals, which is not our case. Our case is water and one metal. You have the mass of each, 2 kilogram and 3 kilogram. You have the specific heat of each. One is 1000 and one is 1500. I would love to compare to what we have in this table. So we're talking about 1000. So it's like a bit bigger than this, than the metals we have in here, because I cannot remember anything in the literature around 1000 and 1500. I know the initial temperature of each. This is cold and this is hot. Okay. What I know is that the Q's are going to be equal and opposite. And I know that they're going to have the same final temperature. So we're done. We write MC delta T for the first one, knowing the given. We write MC delta T for the second one. We know the given. You're going to help me write the given. And eventually, we're going to write that like Q1 and Q2 are equal and opposite. Any volunteer to help me write the given for metal 2? Just the given, easy. Any volunteer? Just unmute and talk. No volunteers? Tab, you can volunteer on the chat. Tell me, what is T initial?
Yes, Professor.
Okay. Yes, George. So what's T initial of metal 2?
So T1 is 8.
Okay, so this is 80 degrees C. I'm gonna call it T initial. For metal 1, it's 20 degrees C. For metal 2, it's 80 degrees C. T final is also a question mark. So this is Q1, this is Q2. Do you have a calculator, George? All right, so I'm gonna write 2 times 1000. It's already written, I know. Okay, times TF minus 20. And as you can see, they're using degree C, is equal to, because I want to make them equal and opposite, to minus, what's M2? 3 times 1500, okay, times TF minus 80. Okay, the question is to find TF. I'm gonna be silent for 1 minute or two. We'll do the calculation myself. And you can do the same. I got an answer, but I do a lot of calculation mistakes. I will wait a bit so you provide me with your own. T final equals to. So I expect you to write the answer in the chat. Yes, I got the same answer, Clara. Okay, same with me. I'm gonna write 62 degrees C, right? For the other students, just check that you did not do any mistake, all right? So, to be honest, I don't like this equation because it gave me so many troubles back in the past. What if I have 3 objects together? What do I do? The Q's are equal and opposite. It doesn't make sense. Usually I used to do the following. I used to put 2 systems, like check which one is losing, which one is gaining. The one losing the heat, we will put them on the right-hand side. And the ones gaining the heat, I'm gonna put them on the left-hand side. And sometimes it's awkward and you cannot tell who's gaining and who's losing. And sometimes you have ice where you need to do MC delta T for ice and then MLF for it to melt and then MC delta T because you don't know the final temperature, and mess is gonna happen very easily. So the best way, and I don't recommend that you use this, the best way is to use something very similar. So it's not like I'm creating an atomic bomb. I'm just saying if you do Q1 plus Q2 is equal to 0, this will guarantee that you don't have to think which one is gaining and which one is losing the heat, especially if you have 3 objects. You simply do Q1 plus Q2 plus Q3 equal to 0, irrespective of who's losing, who's gaining, and what's happening. And it works, okay? Just keep that in mind because I know if you're gonna cover this in the course, and I think you're gonna do that, it's gonna get really complicated in the problems. Now the experiment. I will use this diagram to explain the experiment. The experiment is very simple, you will see, and the lab is very simple. I have a metal. Do you see the metal? Yes. I think I'm gonna use copper, steel, tungsten, aluminum. This is what I'm trying to remember. Definitely not 4 objects, probably only 2. And the results, if you want, the results are here. They actually use tungsten and just a second. This was not active. Okay, so tungsten and copper. Copper is obviously reddish and tungsten is like aluminum, but not so white. So it's gray. Yes, I know aluminum is very light, but those are gonna look a bit like each other. Tungsten is a bit big. I don't know. This is the same. I'm trying to remember shape versus mass because both samples were gonna be 200 grams. I remember tungsten was bigger in size. Bigger mean less dense because you need a big size to create 200 grams. Anyway, we're gonna see the video together. The solid is gonna be hot. How can I heat up my solid? I need ideas. I have a piece of copper, like a cylinder, like the shape of a battery cylinder, this size, and I want to heat it up. What do I do? Any ideas? You put it on fire directly. No, it's not gonna melt because you need really higher temperature, but probably it's not gonna heat up evenly, but why not? Why not? Because we're talking about a cylinder that is thick. So what I will do, I'm gonna put it in boiling water, all right? So, because I know if I put it for a long time or a reasonably long time in boiling water, inside boiling water, it's gonna end up, and let me change that to black, it's gonna end up having a temperature very close to 90 or 100 degrees here, all right? And this is what I'm gonna do. I'm gonna put my cylinder in boiling water and wait while water is boiling. Eventually, thermal equilibrium is gonna happen between the solid and boiling water. But I don't want you to get confused. Boiling water is not part of the experiment. It's only to heat my solid, and I'm supposed to heat my solid before the experiment, okay? I can take the temperature of the hot solid, which is the same as the boiling water. Sometimes 90s, you know, because water is not pure water, it's gonna boil around 95 or 98, probably not 100. Whatever you do the measurement. I did not show you the thermometer, but probably I'm gonna show you in the results, or probably I'm gonna use temperature. It's already rounded for you, 2 significant figures. So who did the measurements and how, using which measuring tool? They already gave you the uncertainty, and I'm upset because I wanted you to guess, but it's okay. I think you know how to guess and why ask you always to guess. All right, so this is T initial. I'm gonna call it T1. This is water, right? I'm not gonna call it cold. You can call it cold if you want, but it's room temperature water. You can measure the temperature of it. This is system 1 and this is system 2, okay? You're gonna put them together. You're gonna do that inside the calorimeter to make sure that everything is well insulated, because you know, otherwise you will have heat escaping to the environment and your final temperature is not gonna be accurate. Can you tell me now, who gives heat to who? System 1 to 2 or 2 to 1? So we have heat exchange between system 1 and system 2. How does it happen? From 1 to 2 or 2 to 1? Can you hear me? Yes, obviously it's gonna go from 1 to 2. So 1 is gonna lose heat and 2 is gonna gain heat. And I can simply say Q1 plus Q2 is equal to 0 because they're equal and opposite. And I can, no melting is happening, no boiling, no evaporation, nothing. I can say MC delta T for the first one is equal to MC delta T for the second one. The same T final is gonna happen, okay? And we can solve for T final. I remember that water is approximately 100 grams in the experiment. And I remember that the solid is 200 grams in the experiment. And approximately, I'm trying to give you some values. For the temperature, the solid was very close to 95 degrees and the water was very close to 25 degrees. Can you guess what is the final temperature? Actually, the final temperature will be measured and the question mark will be find C of the solids. That's the question mark. They don't want the final temperature because you can wait and measure it. It is easy. So, can you guess what would be the final temperature? Knowing that the solid is a metal and you have an idea about the specific heat capacity of the metal. I can tell you that the mean of these two values is going to be 25 plus 95 divided by 2, it's 60. Do you think the final temperature is going to be above 60 or below 60? Below 60, Mia. Can you give one reason why? And if anybody has a different answer, please speak up. Mia is saying that water heat capacity is very high, so the final temperature should be closer to the water temperature. However, Mia, and how do you explain this? We're talking about only 100 grams of water and 200 grams of the solid, so it's double the mass. Do you think still this is gonna happen? All right, so we don't know. Or you can simply discuss the fact, let's say we're talking about copper. Copper specific heat capacity is not even half the one of water. So even if you're talking about half the quantity of water, it's still so powerful because the specific heat is around 3 times more. No, actually even more. What's 4 divided by 0.4? 10 times more. Imagine. 10 times more. Water is 10 times more. So if you want your final temperature to be exactly in the middle, you need copper in mass 10 times more. Twice is not enough. All right. So your answer that says below is totally right, Mia. Yes, it's important to guess sometimes because this is your best understanding of how things work. Now let me show you the lab report. The lab report, you will be given 2 metals and you have 3 trials of each. So except something like average and RMS to do. The best, actually the final answer, the question would be to find the specific heat experimental of the solid. You will be asked to find the theoretical one anyway. For copper, you can find it in the slide. For tungsten, you can Google it. Let me see if tungsten is here. It's not. Let me see if tungsten is here. It's also not. Just Google it. You can find any value and compare it to the experimental value. You will be given some questions like calculate the average, compare to your finding to expected value, sources of errors, and this is a general question about water. That's why I was discussing water in the first few slides. These are the results. If you want to take a screenshot, or probably you can watch the recorded video, or I can simply send it to you on Blackboard. What else? Now the video is open here. I'm not gonna watch it with you, obviously. I'm gonna scroll through it fast forward and eventually send you the link so you can watch it. Yes, so you can see here, this is the same device I use to boil water, and I have a thermometer inside waiting for the water to boil, and I put it on and I put the temperature, the power on max because I don't want to wait forever. And the temperature was initially 45 and I was waiting for it to be close to 100. These are the 3 samples. This is copper, this is tungsten, this one probably steel. I think I'm gonna say it in the video, but I can't remember. And you see it's attached by a wire because I want to handle with care. Boiling water is very difficult to handle on your skin. So I'm gonna plug the small one because small is easier to handle inside water, and you see the wire is outside because I want to remove it. And you know, removing your solid from the water is a source of error because it's gonna cool down on the way before you put it down in your other sample. This is a calorimeter, which is basically a foam cup, but trust me, it's an excellent insulator because you have a column of air outside between the plastic cup and the foam cup. And air is an excellent insulator, one of the best. And you know, the specific heat capacity of air is very low. Do we have it in this table? Do you see air or something? No, but it is very low, which means actually very high, which means heat cannot escape easily. Okay. So, and this is my system 1 or system 2. It's 100 milliliters. So this is a way to measure it. And you see, smallest subdivision divided by 2. This is not very precise. So it's approximately 100 milliliters. I'm using the density of water to calculate the mass because my spring scale is broken. This is also, I'm losing precision. But it's not bad, you know. It's gonna be pretty fine. This is the temperature of system 1, the water. Temperature of the solid, I don't know yet. I will put the water inside the calorimeter and wait for the solid to heat up. Now the solid is hot probably. It's this is 100 degrees, this is 90, this is 98 or 97. I think I can remove now the solid. I will remove it. Does it show where is the solid? I will remove it and put it in my water. I will do that now. Remove it quickly, put it in the water and close quickly. The thermometer here is to find water, the final temperature. So now I have solid and cold water together, system 1, system 2. Please ignore boiling water. It's not part of my experiment. It's only to heat up my solid before the experiment. And this was a big mess for the students that I had on the benches. ما كانوا يعرفوا أيهو system 1 أيهو system 2 في system 3 اللي هو boiling water, and they used to measure the mass of it. شو خص, we don't care about it. It's only to prepare my stuff. We don't need to close it well, but yeah, I was closing it well. T final, I need to wait a bit. So it was initially 20 and it's gonna raise to 37. Was it the final temperature? 35, 40, 46, depending on the initial temperature of water. As you can see, the initial temperature of water was 25. In trial 2, it's a bit hotter because apparently the students here did not want to wait for the sample to cool down because it takes time for water to cool down. So they started the experiment. After heating up the solid again, they took T initial of the water just before they put them together. So they didn't really care if what was hot and cold, and it doesn't matter because you need that for your calculations. And you can see that T final is going to be affected, but C of the solid is going to be the same if you do the calculations. Yes, back to the video. And that's it. So I'm going to wait a bit to find T final. Let me see in the video, you see the temperature is increasing. It was below 20. We did that a month ago. It was actually cold. So it was around 18 degrees C, but you don't know tap water. It could be anything. We waited a bit. Where is it? It's still not even 25. I think that's it for this experiment, not the results you have. And here I'm going to repeat the same experiment for copper. Okay. You can easily throw sample 1 and get a new sample 1 fresh and do the experiment again while waiting. Like I'm waiting for this one, but boiling the copper. I think it's going to reach 25, probably 26, not more. And that's it. The experiment is easy. It's a bit time consuming. Why? Because you need to wait for the solid to boil and wait to find T final and repeat it 3 trials for each solid. So a total of 6 trials. 6 times 15 minutes is how much? It's 90 minutes. That's you doing the work. That's if it only takes you 15 minutes, but sometimes you will have problems and you have to repeat. And sometimes it takes you less if you understand the trend of what to do and how. Yeah, so it was a time-consuming experiment, but yet very easy. So now that you have the results, I think the lab report is going to be a cookie for you, like a piece of cake. Okay, I'm going to save this. I'm ready to answer any of your questions. I will post the results. I'm not in a hurry. I'm very busy this evening with 2 deadlines. Probably post tonight or wait a bit, a day or 2. The more I wait to post the results, the more I push the deadline, which is good for you, I believe. So if anybody is bothered by the fact that I'm delaying your work, just let me know. I can simply send you the work on the private message, okay? Because everything is ready anyway. Any question before I leave you? I'm sorry for that. Yeah, any question before I leave you? All right, you are welcome to leave, but please stay behind if you have any question. You too.